In this last series of videos, we're going to take a look at some of the finer details of electrophilic aromatic substitution. And we're going to also try to tie up some loose ends that will hopefully help us better understand EAS in the context of organic synthesis. We're going to start by taking a look at phenol and aniline. Phenol is the benzene ring with a hydroxy group on it. Aniline is a benzene ring with an amino group bonded to it. And I want to take a close look at these two reactions because I think they illustrate how active the hydroxy group and the amino group both can make that benzene ring. How much those groups activate benzene towards electrophilic aromatic substitution. So in both of these reactions, the starting material is treated with bromine, and then the reagents underneath the arrow are acting as the solvent. So with phenol, it's ethanol and water. With aniline, the solvent is acetic acid. In both of these reactions, we're making the 2,4,6 tribrominated product. So you can see that substitution occurred in both ortho positions and the para position in both reactions. It's important to note that whenever you do a single bromination, whenever you add a bromine to that ring, that's going to deactivate that product a little bit relative to the starting material. So each subsequent bromination should be slower and slower. What I really want to pay attention to is the lack of Lewis acid in either of these reactions. And this is really what illustrates the activity of both of these starting materials. Is that we can get electrophilic aromatic substitution to occur without forming some really high energy electrophile, right? The phenol can react with bromine on its own. The aniline can react with bromine on its own. And both of these reactions illustrate also the regioselectivity of substitution. However, if we're using electrophilic aromatic substitution for synthesis, perhaps we don't want to add 3 bromine atoms to our phenol or aniline starting materials. Maybe we just want to add 1 bromine, right? Maybe we just want to functionalize 1 position around the ring. Well, with phenol, this is a fairly simple process. What we do is we start with phenol, and we treat with bromine, just like in the previous reaction. But in this case, we're going to use the solvent carbon disulphide and run this reaction at less than 5 degrees Celsius. And if we stick to those conditions, we should be able to form as the major product the para-substituted phenol, para-brominated phenol. Now what's going on here? So carbon disulphide is structurally similar to carbon dioxide, so it's a linear molecule. And you can imagine that this is a non-polar solvent. If you think about what's happening in this reaction, in order for the reaction to take place, we have to form an ionic intermediate. Ionic intermediates are not going to be stabilized very easily in a non-polar solvent, right? The solvent will not be able to interact very much with that ionic intermediate. As a result, this is going to significantly slow down the reaction. So much so that we should be able to preclude multiple brominations, as long as we're careful and we monitor the reaction. Right? Since the reaction is being done at less than 5 degrees Celsius, right, so pretty cold temperatures, the reaction rate of this bromination should furthermore be reduced, right? When we cool down reactions, we're slowing down how fast those molecules are moving and how often they interact. And therefore, we're going to slow down the rate of the reaction. Right, so that solves our problem with polybromination of phenol. I will mention that in this reaction we will also make a somewhat significant amount of the orthobrominated product, but in this case the parabrominated product will be made in the majority. All right, if we try this with aniline, same conditions, so bromine, carbon disulphide, less than 5 degrees Celsius, so cold temperatures, we still see the polybrominated aniline. And this really speaks to the reactivity of that amino group, particularly relative to the hydroxy group, right? Nitrogen is more willing to give up its electrons, its electron pair, right? It's a better nucleophile in most cases. And in this case, it's a better activating group for that benzene ring. All right, so we will come back to this reaction, but I want to look more at phenols before we move on to anilines. Right, so we can actually, there's a pretty useful reaction that we can do with phenol. That was actually the basis for one of the first laboratory syntheses of the drug aspirin. This was invented in Germany. It's a reaction called the Colby Schmidt reaction. A lot of the early name reactions were developed in Germany, which is where many of the chemistry developments were occurring in the early 1900s. So this reaction starts with phenol. And this is actually going to be an electrophilic aromatic substitution that happens under basic conditions. And so in this reaction, we're going to treat with potassium hydroxide, carbon dioxide, and heat it up. And then we're going to work up that reaction with acid. I'll just say H plus workup. And what we get out is the compound salicylic acid. Right, if we take salicylic acid and we treat this with acetic anhydride or acetyl chloride, and we can use a base as well, but we'll just show the acetylation in simple form. We'll acetylate the hydroxy group. And then we have our carboxylic acid, and this is called acetyl salicylic acid. Mechanistically, what is happening is the hydroxy group from potassium hydroxide is going to pluck off this proton. And we're going to create a phenoxide anion. Right? You can imagine if phenol is an activated arene, phenoxide would be very, very activated. And in fact it is so activated that it can, kind of with the help of sodium, which is kind of tying these things together, those electrons can fall down, kick a pi bond out, and shoot electrons up to oxygen. Right, now we've made a carbon-carbon bond. right? You can see we've installed our carboxylate group, and then since we're in base, we could take hydroxide, pluck off that proton, re-aromatize, right? And then when we work this up with acid, we'll protonate the carboxylic acid, and we will protonate the phenol. Right? So this was actually used on an industrial scale. It's a very good reaction. You really have to heat it up. It helps to also use high pressure carbon dioxide. But it was a reaction that helped in the production of aspirin as a medicine. All right, so let's shift gears and take a closer look at aniline now. All right, so we've already established that we can't adjust the solvent and adjust the temperature to reduce the activity of aniline low enough that we just get one bromine added to that molecule. All right, so what can we do? Well, the strategy that we will take is we will treat aniline with acetic anhydride. And just like acetic anhydride was an acetylating agent up here for the oxygen, acetic anhydride will be an acetylating agent for nitrogen. So now we have an N-acetyl aniline. Well, what is this doing? Well, this is taking those lone pairs of electrons, right, which are still, different color here, still donating into the ring, right? So this is still an activating group, and it's still an ortho-para director because there's an atom with a lone pair of electrons sitting right outside of the ring, right? But these lone pairs of electrons can also donate into the carbonyl, right? And as the oxygen is an electronegative atom, it's actually probably better for those electrons to move up towards oxygen than they would be to move into the ring. So even though this is still an activating group and still an ortho-para director, it's significantly less reactive than aniline because we're putting on a group that's distracting those electrons away from the ring. All right, so we can take this N-acetyl aniline, and now we can treat it with bromine and acetic acid. And when we do that, we get the addition of one bromine in the para position as the major product and no bromines in the ortho position. You can imagine when we add this acetyl group and we have somewhat free rotation around that carbon-nitrogen bond, that acetyl group is going to be swinging around on both sides of that benzene ring and kind of blocking the ortho substitution from occurring. To remove that acetyl group, see if you can think about how we would get back to the amine. Maybe pause the video, try out a mechanism, try out some reagents, and see if you can figure out how we get back to the para-bromoaniline. Well, if you paused the video and thought about this, hopefully you identified this group as an amide. And when you hydrolyze amides, you break the carbonyl-carbon nitrogen bond and make a new carbonyl-carbon oxygen bond, and then you end up protonating that leaving group in the end. So for this, we can use acid, sulfuric acid, and we'll use a mixture of ethanol and water. Right? Both are going to act as a nucleophile and displace the amino group whenever this carbonyl is protonated. The reason why we're using ethanol is because we're probably going to need something organic to dissolve this molecule. It's doubtful that it will be water soluble. So we'll use an organic alcohol to help bring that molecule into solution. When we do that, that kicks out our amine, our parabromo aniline, and then a mixture of acetic acid and ethyl acetate from the addition of water or ethanol to the carbonyl.